And what a beautiful, crisp October morning it is in Grinnell, Iowa. I'm Joanne Bundy, and the Planning Committee joins me in welcoming you to the 7th and last class of our Variety Pack. You will notice that you have half sheets of blue paper on your table this morning, and that is your opportunity to give us suggestions and feedback about the bucket courses and the Variety Pack in particular. And it isn't a requirement, but the Planning Committee likes to do the best we can possibly do for the bucket courses, and your suggestions are very helpful to us in being able to do that. So feel free to fill those out. Just leave them on the table in the hallway, either at halftime or after the class. Please silence your cell phone and turn on your tea coil. I think there were a lot of us last week who hadn't been familiar with Knut Hamsun, but today a lot of you have heard about Niels Bohr, and that's thanks to Prof, who has given us a little background on him from time to time. And today, Niels Bohr was an extraordinary scientist, and today we have an extraordinary teacher to tell us all about it. I am delighted to welcome the Professor Emeritus of Chemistry at Grinnell College, Luther Erickson.
Thank you for that generous introduction. Happy to see all my friends here. I think I know 90% of you. So, when Joan Bundy invited me to contribute to this bucket course series of biographies, I decided to discuss one of the giants of 20th century science, whose early work served as a key link in the development of our understanding of the atom, the fundamental building block of matter that 19th century chemists had identified. My subject is Niels Bohr, Danish physicist born in Copenhagen in 1885, who contributed significantly to our understanding of both atomic and nuclear physics in the first half of the 20th century, and is often compared to Isaac Newton in his influence. My special affinity for Niels Bohr can be traced to a lecture that he gave at the University of Wisconsin in 1957, near the end of his illustrious career, while I was still a graduate student in physical chemistry at the university. The lecture was scheduled for 3 o'clock in the afternoon in the lecture hall at the physics building, which was just up the hill from the chemistry building where I was housed. My lab mate and I made the trek up there, and by the time we got there, it was revealed that the lecture had been moved to the Union Theater over Bascom Hill and down by the lake. So we tore down there as fast as we could go, but we didn't get there to get very good seats. In fact, I sat in the top row of the upper balcony at the Union Theater for this lecture. Well, Niels Bohr is not an outstanding public lecturer. In fact, he tends to mumble and speaks in a sort of broken Danish, broken English with a lot of Scandinavian accent. So I must confess that I didn't understand a word of each what he said. But it was a wonderful event.
Yes.
So, in order to understand Bohr's life and work, it'll be necessary to construct, in parallel with some of the details of Bohr's life, what I like to think of as a biography of the atom. Those tiny particles that collectively make up the world around us. Bohr's initial contribution came just over 100 years ago with the 1913 publication of his model of the hydrogen atom as a miniature solar system with a single negatively charged electron rotating in one of several circular orbits around a much more massive positively charged proton. Interest in the nature of matter goes back to ancient times. Aristotle suggested that the four elements, earth, water, air, and fire, could account for the variety of materials we found around us. The elements were pure but could not be found in that state on Earth, and every visible thing was made up of some combination of these. Well, that classification proved to be limited in its usefulness, but it's quite similar to the classification that we still find appropriate in trying to describe the world around us, especially geological and meteorological phenomena, namely a world of solids, liquids, and gases that can be interconverted by supplying or removing energy. So in the 18th century, investigations of the European scientists, especially the French chemist Lavoisier, who discovered nitrogen and is sometimes regarded as the father of chemistry, and Joseph Priestley, who discovered oxygen, and others, enabled the British scientist John Dalton to formulate his atomic theory for the structure of matter in the early 1800s. Dalton's atomic theory can be summarized in the following three statements. Elements are composed of extremely small particles called atoms, like hydrogen, oxygen, carbon. All atoms of a given element have identical properties which differ from the properties of other elements. Components or compounds are formed when atoms of different elements combine with one another in ratio of small whole numbers. And so we were able to write things like H2O for water and CO2 for carbon dioxide and CH4 for methane and so on. So by the 1870s, a consensus was emerging about which substances are truly the elements from which all the other substances can be constructed. About 60 elements have been identified by this time, and when these elements are listed in the order of increasing atomic mass, interesting regularities in the variation of certain properties became evident. So Dmitry Mendeleev in Russia and Lothar Meyer in Germany were the first to call attention to these regularities with the construction of what we now refer to as a periodic table of the elements. Mendeleev quoting here, "In a dream I saw a table where all the elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper." And this is a dressed up version of Mendeleev's first periodic table. The blue elements here are elements which were actually included in the table. The pink ones weren't even discovered at that time, but he was able to arrange them in an orderly fashion, and in fact predicted that there were other elements would be found for the gaps that were in the table. Since the early efforts of Mendeleev, several additional elements have been discovered. And in the 20th century, the availability of neutron sources and nuclear accelerators have led to the preparation of many short-lived elements, even heavier than uranium, the heaviest element known to Mendeleev. Nevertheless, the notion that the composition of ordinary matter can be described by specifying the identity and relative amounts of elements included in the periodic table was well accepted by the end of the 19th century, when Niels Bohr was still a schoolboy in Copenhagen. A half-century later, in no small part due to Bohr's initial work and his encouragement of fellow scientists, the detailed composition, structure, and properties of individual atoms was established. I'm just going to point out a couple of things here of interest. This is the fully expanded periodic table with all the known elements, including a whole bunch that have been synthesized after the development of nuclear energy. Uranium is up here, 92. Things like berkelium. There's one up here. I'm trying to find bohrium. Yeah, there's bohrium. So one of the elements was named appropriately after Bohr. I'll touch on some highlights of that voyage of discovery this morning, but first let's get better acquainted with Niels Bohr and one of the leaders of that voyage and the subject of this sketch. Niels Bohr was born October 7th, 1885 in Copenhagen, Denmark, to Ellen Adler, who was part of a successful Jewish banking clan, and her husband Christian Bohr, a celebrated physiology professor at the Institute of Medicine at the university. Niels had an older sister, Jenny, pictured here with her parents, and a younger brother, Harold. The family lived in generous quarters provided for the faculty of the Academy of Surgery, where his father was professor of physiology. Christian and Ellen Bohr became the beloved center of the constantly growing circle of intellectuals who were guests in their lovely home in the Academy. It's certainly no exaggeration to say that Niels and Hare grew up in a home in which was not only intellectual, but which also among the most distinguished in outlook and humanity. So this is the home in which this is the academy where they had living quarters. Christian and Ellen Bohr were, to a rare degree, able to give their children an education which provided the widest possible scope for their independent development, while at the same time developing their sense of cultural and human values. Niels and his younger brother, Niels outlined here in yellow, went to the Gammelholm Gymnasium. The boys were almost 2 years apart in age, but only a year apart in school. Both were physically active and athletic and learned to play soccer when it was introduced in their school about this time. The younger brother, Harold, became very proficient at soccer and even played on the Danish Olympic soccer team that won a silver medal in the 1908 Olympics. Here are the brothers at various stages in their lives. There's the roster of the 1908 Danish Olympic soccer team, football team. Football meant soccer in that sense. The two brothers were very close throughout their lives and both went on to Copenhagen University, where Niels found his way into physics after pursuing philosophy initially, while Harold pursued a degree in mathematics. In 1907, Niels completed his BA degree and was awarded a gold medal from the Danish Academy of Science and Letters for his paper on a new method for determining the surface tension of water. In 1909 and 1911, he had continued on to obtain his master's degree in 1909 and his doctorate in 1911. His thesis, based on the work on the physical properties of the metals and their interpretation in terms of the properties of the electron, which had been discovered only a short time earlier by J.J. Thomson in England. Like many aspiring academics, Niels followed up his graduate degrees with postdoctoral study with another researcher in a field that would expand on his graduate degree work. Niels chose to work with J.J. Thomson at Cambridge University in England and later Ernest Rutherford at Manchester, where he developed his model of the atom, which was published in 1913, was ultimately recognized with a Nobel Prize awarded in 1922. Between the Cambridge and Manchester years, he married Margaret Norland, the younger sister of a pair of Norland brothers who were close friends of the Bohr brothers, Niels and Niels and Harold. The couple would have 6 children, 4 survived to adulthood, and one, Oa, pronounced, it's spelled A-A-G-E, but pronounced Oa, would become a well-known physicist like his father. So I'll take you through some of the background that led Bohr to develop his planetary model of the atom. About the time he was getting started, there were lots of things going on in physics and lots of puzzles. Just listing some of them here: the photoelectric effect, black body radiation, line spectra from atoms, radioactivity, X-rays, the electron. These were emerging about this time. So I'll take you through some of the background that led to Bohr to develop the model, and then I'll return to identify some additional highlights of a very full life, including his establishment of the Institute for Theoretical Physics at the University of Copenhagen, which became a magnet for atomic and nuclear physicists from all over Europe and the world, and continues to this day to be among the outstanding research institutes in the physical sciences. In the 1930s, Bohr made important contributions to the understanding of the properties of the nucleus and clarifying nuclear fission processes that permitted the development of nuclear energy in World War II. Finally, his leadership efforts on behalf of the Jewish scientists in Europe and the Jewish citizens of Denmark in World War II, the development of the nuclear bombs at Los Alamos, and responsible exploration and use of nuclear energy during and after the war were impressive contributions to international cooperation in the post-war period. Okay, one of the first clues that the immutable atom of Dalton was not quite so simple was the discovery by the French scientists Henri Becquerel and the Curies, Marie and Pierre, that some elements spontaneously emitted charged particles or penetrating radiation independent of their chemical composition or prior treatment. Further research revealed that three distinct types of radiation labeled alpha, beta, and gamma could be identified. Alpha rays were found to be positively charged, comparatively heavy and not very penetrating. Beta rays were negatively charged and light, and proved in fact to be identical to the electrons that J.J. Thomson had later discovered in his study of cathode rays. Finally, the gamma rays were not deflected by electric or magnetic fields at all, so they were not charged particles at all, but high energy electromagnetic radiation with higher frequencies and shorter wavelengths than visible light or even UV radiation. So Becquerel and Curie shared the 1903 Nobel Prize in Physics for their discoveries. Marie Curie was later awarded a Nobel Prize in Chemistry in 1911 for her discovery of the radioactive elements radium and polonium. Shortly after the discovery of radioactivity, J.J. Thomson, the son of a Manchester bookseller who entered college at 14 and at 28 was elected a Fellow of the Royal Society and appointed to the chair of physics at the Cavendish Laboratory at Cambridge University in London, made the next critical discovery. During the course of his investigations of the properties of cathode rays, he provided convincing evidence that the rays consisted of charged particles which he called the electron. He measured with his device the ratio of charge to mass for these electrons and was able to estimate that the mass was equal to about 1/2000th the mass of the hydrogen atom. So these were very light particles and a small part of the mass of an atom. American Robert Millikan, who was born in Illinois and went to high school in Maquoketa, Iowa, attended Oberlin College before pursuing a PhD in physics at Columbia, also made a significant contribution to this whole process. He determined a really sound method for determining the charge on the electron, and with the ratio of mass to charge, the mass could be determined. Before we move on to describe Bohr's contribution to the understanding of atomic structure, three additional related phenomena deserve our attention. To follow the subsequent developments, it's important to have a rudimentary appreciation of electromagnetic spectrum and the focus of many experiments in atomic physics. The familiar rainbow colors of the visible light spectrum are just a tiny fraction of the wavelengths available in the whole spectrum, which ranges from the very short wavelength gamma rays and X-rays to the very long wavelength radio waves with a million, billion longer wavelengths. So, summarizing what we know at this point, the proton has a relative mass of 1 and a positive charge of 1, plus 1. The electron, very much smaller mass and a negative charge. So those are components of the atom that we didn't know about until these experiments. Now let's go on to consider this picture. The key analysis of the radiation emitted by heated objects by German physicist Max Planck, symbolically reported in 1900, altered the way radiation is viewed and introduced a key concept essential to the interpretation of spectral data and atomic structure in the 20th century, which was about to begin. The distribution of energy emitted by an ideal black body. A black body is one which is in equilibrium with the radiation that's bouncing off the walls and approximated by building a box, painting it black inside, and making a tiny hole. Now you heat that up and you examine the light that's coming out. This is black body radiation. Well, that's a function of temperature, as anybody knows who's heated up any metal and seeing it go red hot and then white hot and so on. So it shifts, the frequency or the wavelength maximum shifts as you go to higher temperatures. Planck was able to derive an equation to describe the distribution of light for the heated body only by assuming that the energy of the light at a given wavelength is proportional to its frequency. The proportionality constant is referred to as Planck's constant, and the interpretation leads to the identification of the photon as a discrete kind of packet of light whose energy is equal to h times the frequency. And this derivation enabled them to get away from the problem with classical physics that suggested that shorter wavelengths should be more and more probable, and so there should be more energy in the shorter wavelengths than the longer ones. That's referred to as the classical theory, and that line that goes straight on up and does not correspond to experiment is referred to as the ultraviolet catastrophe. Well, the evidence that light sometimes behaves like a material particle, yeah, here's a picture of Max Planck, by the way. He won the Nobel Prize in 1918 for this proposal. In 1948, the German government, the society, Max Planck Society, was founded to support German scientific research. Currently, there are 82 Max Planck Institutes in a great variety of scientific fields, not only in Germany. The most recent ones, Max Planck Institute, Max Planck Florida Institute in Neuroscience was established in 2008. So we are benefiting from his heritage. The evidence that light sometimes behaves like a material particle was further demonstrated by the photoelectric effect, the phenomenon responsible for the functioning of a photographic light meter. When light shines on a metal surface, electrons may be ejected and current flow in the circuit shown. The energy of the electrons depends on the energy of the light photons, which depends on the frequency. And Einstein, taking that lead from Planck, suggested that the photons can have an energy equal to h, Planck's constant, times the frequency, because short wavelengths will produce a photoelectric effect, but as you go to longer and longer wavelengths, you get to a point where nothing is produced. Ernst Rutherford, born in August 30th, 1871 in New Zealand, the fourth child and second son of a family of 7 sons and 5 daughters. His father, James Rutherford, a Scottish wheelwright, emigrated to New Zealand with Ernest's grandfather and the whole family in 1842. Educated first in New Zealand, he won a scholarship to go to Trinity College, Cambridge, as a research student, and eventually found his way back to Manchester. So in 1910, he directed the investigation that led to the next breakthrough in sorting out the structure of the atom. And this is the diagram of the experiment that he carried out. I'll read a little bit about his description of the experiment. One day, in the early days, I'd observed the scattering of alpha particles, and Dr. Geiger in my lab had examined it in detail. He found in thin pieces of heavy metal that the scattering was usually small, the order of 1 degree. One day, Geiger came to me and said, "Don't you think young Marsden, whom I'm training in radioactive methods, ought to begin a small research?" Well, I thought so too, and so I said, why not let him see if any alpha particles could be scattered through a large angle? Well, I may tell you in confidence that I did not believe they would be, since we knew that the alpha particle was a very fast, massive particle and a great deal of energy, and you could show that if the scattering were due to the accumulated effects of a number of small scatterings, the chance of an alpha particle being scattered backwards was very small. Then I remember 2 or 3 days later, Geiger coming to me in great excitement and saying, "We've been able to get some of the alpha particles coming backwards." It was quite the most incredible event that's ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. On consideration, I realized that the scattering backward must be the result of a single collision, and when I made calculations, it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute nucleus. So that's the backward scattered one that shouldn't have happened, but did. So when Niels Bohr went to England for postdoctoral research in physics in 1911, he chose to go to Cambridge and work with Thomson, who had discovered the electron. After a year in which he could scarcely get Thomson's attention to review his doctoral thesis on the electrical conduction of metals, he contacted Rutherford at Manchester and was able to get support for a year there. He and Margaret were married on August 1st. Of 1912, they settled in Manchester for Niels to work with Rutherford. During that year, he came up with his planetary model for the atom, starting with the simplest atom, hydrogen, with one negatively charged electron moving around a single positively charged proton, which contained almost all the mass. He further assumed that the electron moved in a circular orbit whose radius is determined by balancing between the centripetal force of the moving electron and the electrostatic attraction between the positively and negatively charged particles, and limits on the angular momentum. The calculations introduced a quantum number n to describe each orbit from n equal 1, 2, 3, and so on. The radius of each orbit was calculated to be proportional to n squared. The first few orbits for hydrogen are shown here. Bohr made the further assumption that electrons in those orbits do not radiate any light, but transitions between the levels that give rise to the characteristic lines observed in the hydrogen spectrum, observed in a hydrogen-filled gas discharge tube. So by setting the calculated energy difference between levels to h, Planck's constant, times the frequency again, the quantum condition that Planck used to describe black-body radiation, Einstein to fit the photoelectric phenomenon, he could calculate the wavelengths of light expected. In fact, he generated this equation that 1 over the wavelength is equal to some constant called the Rydberg constant, and 1 over 2 squared minus 1 over n squared, where n can take on these different values. Not only that, he calculated on the basis of the model that the Rydberg constant should be 2 times pi squared times the mass of the electron times the charge on the electron to the 4th, divided by Planck's constant to the cube, and the speed of light. And that matched exactly the experimental results observed when you have a hydrogen discharge, pass the light through a prism, and record the spectrum on a photographic film. The hydrogen spectrum in the visible part of the spectrum is amazingly simple. 4 lines, a red, a green, a blue, and a violet. And the frequencies calculated by Bohr's model agreed exactly with those experimental values. The model also predicted longer wavelength transitions in the infrared and shorter wavelengths in the ultraviolet, which were ultimately revealed by other researchers after Bohr's report. The model was often subsequently referred to in the literature as the Bohr-Rutherford model, in acknowledgement of the importance of the alpha scattering experiment that established the extremely small size of the nucleus. So, Bohr then went on to extend the model to multi-electron atoms and to relate the calculations to the organization of the atoms in the periodic table. So for multi-electron atoms, that's all the rest of them, each of these levels can accommodate increased numbers of electrons as suggested in this figure. So we got a series of levels, a series of shells, as it were. The first one can hold 2 electrons, the next one 8 electrons, the next one 18, the next one 32, and that matches up with the length of the sections in the periodic table that had been generated years earlier. Alternatively, the electron distribution of the first 18 elements can be shown as here. I should emphasize that the small circle in the middle of each of the atoms, which depicts the nucleus, is much too big to be to scale. See, it's very, very, very tiny. It would be, you can't even show it on the paper. It's so tiny. The nucleus is many orders of magnitude smaller. The atom is mostly empty space, in fact, with tiny massive nucleus and comparatively tiny electrons buzzing around the positively charged nucleus. This picture of Bohr and Rutherford was taken many years later with their wives in Copenhagen, but this collaboration proved to be very fruitful. We're going to jump ahead to a time closer to this picture. In November of 1922, an inquiry came from Stockholm. Would Professor Bohr be ready to receive a phone call from Stockholm the next morning? It could mean only one thing. Bohr was about to receive the Nobel Prize in Physics. The call the following morning confirmed the good news. The prize had not been awarded in 1921, so 2 awards were made in 1922. The delayed 1921 prize went to Albert Einstein for his services to theoretical physics, and especially his discovery of the law of the photoelectric effect we discussed earlier. The 1922 prize went to Bohr for his services in the investigation of the structure of atoms and the radiation emanating from them. It seemed to the Bohrs that the congratulations poured in from all over Denmark. The king and the man who ran the little ice cream stand at the corner below the institute all rejoiced. For Denmark and for Niels Bohr, it was the greatest of honors. The small state had outdistanced the great powers in one of the highest fields of human achievement. The students and fellows drank many a toast and serenaded their friend. It'd be nice to include some pictures of the Nobel Award ceremony in Stockholm on December 10th, 1922, the anniversary of Alfred Nobel's birth. I can't show you such pictures, but I do have a couple pictures from the Nobel Award ceremonies of 1987. Just 25 years ago, a couple weeks ago, when our own Grinnell College graduate, Tom Check, received the Nobel Prize in Chemistry, and his family members, including our Mayflower neighbors, Robert and Annette Check, were there for the event. I think that's a good time to take a break. Is that too soon? Or I could take any questions before we take a break.
So was Rutherford upset when Bohr got the Nobel?
Rutherford got the Nobel Prize in Chemistry shortly after he did his experiments.
Oh, okay.
He was upset that he got the prize in chemistry and not physics.
Well, do your brains feel a little hot? As you know, we have these courses on our YouTube site. And if any of your Mayflower residents are having problems figuring out how to do that on your computer, Jack Gustafson has generously offered to help you with that. So give Jack a call if you need some help. And he will make an arrangement to come to your house and help you on your very own computer. We appreciate that very much, Jack. It's like everything else. It's really easy to do once you know how to do it. So now for the second half with Luther Erickson and Niels Bohr.
That's such a nice looking family shot, we're going to just leave it up there for a while. And that is here, by the way, and most of you know her.
Didn't have much to do with it.
You had all to do with it.
50%.
So, back to Bohr. After spending 2 years as a lecturer at the University of Manchester following his postdoctoral time there, Bohr was appointed Professor of Theoretical Physics at Copenhagen University in 1916. Happy to be back on his home turf, he immediately began campaigning for establishment of an Institute for Theoretical Physics and a structure to house the Institute. He was able to secure funds for the structure, partly from the Carlsberg Foundation, Carlsberg Brewery. The Institute structure included modest living quarters for the director and his family, just as he had lived as a boy in the Institute for Medicine directed by his father, Christian Bohr. And the Bohr family happily moved into their quarters in January of 1921. In the next 20 years, the reputation of the Institute as a major international center for physics research and scholarship became legendary, as it attracted a steady stream of students and researchers at all levels from all over Europe, most of them to interact with the enthusiastic and much respected Danish professors. Bohr in turn frequently traveled to give lectures and meet with colleagues in the rest of Europe and beyond. After Bohr's visit to Cambridge, Rutherford reported that the lectures went well. How well they were heard is another matter. Bohr's voice seldom carried to the back rows, as I can attest. And even those in the first rows sat with ears turned like dish antennas to catch the very low sound. Ever since its introduction, the Bohr theory of the atom was seriously questioned and criticized. In the 1920s, alternative formulations of quantum mechanics were developed by Werner Heisenberg, Erwin Schrödinger, and others who focused on the wave-particle duality reflected in the photoelectric effect and several other phenomena. Oops. You got to be careful what you touch on these computers. Let's look at those guys a while. Bohr participated actively in the new formulations, and the Institute was often the scene of lively debates and discussions for the new directions. Heisenberg introduced the uncertainty principle, which limited the accuracy with which certain pairs of variables, like momentum and position, could be determined simultaneously. The neat circular orbits of Bohr's original hydrogen atom model have given way to orbitals shown as fuzzy probability distributions. Nevertheless, we still envision the atoms as very small units consisting of very dense, positively charged nucleus surrounded by enough negatively charged electrons to balance the positive charge of the protons. The Institute was prospering, and life was good for the growing family of 5 healthy and active sons. They had been living in the director's quarters at the Institute since it was built, but they often escaped to their country home near the coast 30 miles to the north, especially during the summer break. In 1932, the family was informed that they had been selected to occupy the House of Honor, a large and ornate mansion at the edge of the Carlsberg Brewery, built by J.C. Jacobson, founder of the Carlsberg Brewery, and available for life to the man or woman who had brought the greatest honor to the country. After painting and furnishing was completed, the Bohrs left their modest flat at the Institute and happily moved into the house. Their first guests were the Rutherfords from England. I think we showed a picture earlier. And they later hosted the King and Queen of Denmark, and Queen Elizabeth, and Prince Philip of England, as well as many of the greats of science. But it was also a house where the active Bohr boys could pursue their own enthusiasms, and the young physicists from the Institute could come constantly as if they were coming home. Margaret's warmth and graciousness and Bohr's cordial hospitality turned the House of Honor into a home. Those who came always remembered Carlsberg. In 1934, tragedy struck this happy, almost idyllic home. Bohr, his eldest son, 19-year-old Christian, and 2 friends went sailing, as they often did on pleasant summer days. A sudden storm whipped the gray waters into white-crested waves that swept across the deck of the small sailboat and carried Christian overboard and lost. Repeated attempts to recover him from the turbulent waters were unsuccessful, and Bohr had to return to the House of Honor with the dreaded message. In 1932, a key experiment by James Chadwick at Cambridge in London clarified the composition of the nucleus of the atom with the discovery of the neutron. And reactions which changed the identity of elements by bombarding samples with neutrons suddenly became readily possible. Attention shifted from atomic physics to nuclear physics. Here's a sketch of Chadwick's apparatus. He was trying to identify the uncharged radiation which emanated from beryllium when it was bombarded by alpha particles from radioactive polonium, which is back here. When a thin film of paraffin was inserted between the beryllium and the Geiger tube detector, a strong signal from a stream of positively charged protons was detected, from which Chadwick concluded that the radiation coming from the beryllium originally back here was a stream of neutrons, the elusive neutral particle that had been suggested for a long time to account for the extra mass beyond that of the protons in the nucleus of atoms. So, for example, we had ordinary hydrogen with one proton and one electron. But there was another isotope of hydrogen, deuterium, which had twice the mass. And now it's clear that that second part of the mass was a neutron. With the discovery of the neutron, we're now in a position to catalog the composition of any atom, including isotopes, and account for the processes that amount to transmutation of the elements. So here's a small table of the listing for some of the lighter elements, and chlorine, and finally uranium, the number of protons, neutrons in the atom, well, in the nucleus really. The number of electrons outside the nucleus always equal the number of protons. So I'll point out particularly chlorine, which has two isotopes, chlorine 18 and chlorine 20, 35 and 37, which differ in the number of neutrons and account for the fact that the atomic weight of chlorine is not 35 or 37, but somewhere in between, corresponding to the composition. And very importantly for uranium, down here at the end, uranium has two isotopes, uranium-235 and 238. Almost all of the uranium is uranium-238, but a small percentage is uranium-235. And they differ only in the number of neutrons. That ends up having substantial significance for the future. Here's a simple nuclear reaction. Atoms of beryllium-7 with 4 protons, red balls, and 3 neutrons, the blue balls, can be turned into lithium-7 by having the beryllium-7 catch one of the electrons that's orbiting around it. It's a process referred to as electron capture. And then we go from 4-3 to 3-4, and with only 3 protons, that's not the same element anymore, and that's lithium. Well, that's a simple nuclear reaction that transmutes one element into another. Well, Chadwick's discovery provided a method to generate a strong source of neutrons to use in probing the nucleus of other atoms. So unlike the positively charged alpha particles employed in Rutherford's famous experiment that established the planetary model of the atom with a very small nucleus, the incoming neutrons would not be repelled by the positive charge of the nucleus. It was in carrying out such experiments with uranium metal as the target that Lisa Meitner and Otto Hahn in Berlin accidentally discovered nuclear fusion. Fission, I'm sorry. So this is Lisa Hahn, Otto Hahn, or Lisa Meitner and Otto Hahn. And their experiment involved simply having a stream of neutrons, probably from polonium on beryllium, or some reaction that produced neutrons, a stream of them bombarding the uranium, and they were having trouble figuring out what they were getting for product. So they would bombard for a while, and then they would dissolve up the metal and try to analyze to see what new elements might have been produced. Their first attempts suggested that there was a new element produced, and it was radium. Radium is just 2 positions away from uranium on the periodic table, and that seemed like a plausible thing to happen. Well, further investigation established, whoops, it isn't radium. A major product is barium. Now, barium over here has a mass of 141. And if barium is produced, the rest of the mass has got to go somewhere. In this case, a plausible second product is krypton. And the 2 masses together add up close to the uranium-235. Well, actually not quite, because we finally figured out that extra neutrons were being generated. Physics professor Meitner, the first woman to get a PhD in physics from Vienna University, was a physics professor at Berlin, while Otto Hahn was in the chemistry department. They had collaborated before, and in 1938 they began this attempt of the neutron bombardments on uranium. But while these experiments, which I've now interpreted, I guess, were in progress, Meitner went on vacation to Sweden and never returned, for fear of her safety as a Jew in Hitler's Germany. This is 1939. Her nephew, Otto Frisch, was at the time a researcher in Bohr's lab in Copenhagen. The experiments kept yielding a product that they first thought was uranium, finally concluded was barium, atomic number of 56. In December of 1939, Hahn communicated the results to Meitner, who concluded that the uranium nucleus must have broken into 2 large fragments, one part being barium. She communicated that postulate to her nephew in Bohr's lab, and Bohr was about to leave on a trip to America, but he appreciated the significance of the finding and urged Meitner to publish the work promptly. Well, Hahn and his assistant Strassmann got it published, and they won the Nobel Prize in physics. Meitner never was adequately acknowledged for her contribution to the process.
Sounds like DNA.
Yep. Bohr had been working on a theoretical model of the nucleus and suggested how this fission of uranium might be viewed. His liquid drop model suggested that the impact of the neutron might distort the roughly spherical nucleus enough so that further vibration could lead to it breaking into 2 large fragments. Or shown in the second depiction down here, where the individual neutrons and protons are shown, the impact of the neutron gives this intermediate, which is probably agitated and vibrating around and breaks in half, and now we've got 2 big parts. And importantly, as shown here, more than 1 neutron. Here it's shown as 3 neutrons. So that, they figured out pretty quickly, was probably what was going on. Now, the importance of the 3 neutrons here is this. If you have a large collection of this uranium, and I show it here as uranium-235, which turned out to be the isotope which was most readily split by the neutrons, the first reaction would produce 2 fragments and 3 neutrons. And each of those hitting another one would produce 3 more neutrons, and so on, in a chain reaction that, of course, is the basis of a nuclear the nuclear energy revealed in the bomb or power plants every day now. Well, as soon as word of the Hahn-Meitner experiments got out, the possibility of energy production by assembling enough uranium to produce a chain reaction was realized, and a potential of an arms race between Germany and her foes was assured. In 1940, Germany occupied Denmark, in contrast to Denmark and Norway, in contrast to Norway that resisted for 60 days?
62.
62 days. The Danes, seeing that they were badly outnumbered, allowed the occupation to come without any opposition. And World War II was underway. So they tried to adapt to the occupation as best they could. After Hitler came to power in Germany in 1933, the Jewish population in Germany and adjacent countries became concerned about their future safety and livelihood. In Copenhagen, the Danish Committee for Support of Intellectual Workers in Exile was established, with both Niels and Niels Bohr as members. From then on, Niels worked tirelessly to get posts established and have vacancies filled, including in his institute, by these potential exiles. All records of these activities were destroyed in the early morning of April 9, 1940, when the German occupation of Denmark began. In 1941, Werner Heisenberg, one of Bohr's favorites from his postdoctoral years at the Institute and founder of the new quantum mechanics, went to Copenhagen to attend a conference at the Institute. While there, he made 3 visits to the Bohr home. First was quite cordial and not controversial, but something happened during the second visit that aroused Bohr's anger. The third farewell visit was apparently not controversial or substantive. Turned out that Heisenberg was then in charge of Germany's nuclear program. The content of those discussions has been of considerable interest. Speculation even included the suggestion that Heisenberg invited Bohr to support the German nuclear weapons project, since Germany would certainly win the battle for Europe, and Denmark would fare better if they had supported it. Well, the Heisenberg-Bohr visit became the focus of a play, Copenhagen, by Michael Frayn, first produced in London in 1998. Our local community theater performed the play a couple years ago with Mark Schneider as Bohr, Mike Hunter as Heisenberg, and Liz Hansen as Margaret Bohr. And now Ellen Meese will be directing the play at the college later on in November with 4 performances in the Flanagan Theater. There are half a dozen copies of the flyer describing this production, and here's from the top. It'll be November 20th to 23rd, the Flanagan Theater, which holds about 120 people each, so there's a fair amount of seating, but if you want to see the play, you might want to take advantage of getting the tickets early. As described here, winner of the Olivier and Tony Awards for Best Play in 1998, Copenhagen dramatizes what could or should have happened in the mysterious 1941 wartime meeting between the German physicist Heisenberg and his former mentor. So, this is not, the play, well, I'm not going to tell you much detail about it, except that the setting is not the actual setting back there, but is in some afterlife where the 3 of them meet and sort of try to reconstruct what happened. It's a very interesting and very timely play, and I would appreciate her scheduling it to coincide with this lecture. In fact, I didn't know that she was doing this until about a week ago. And she was generously sent me the materials and so on. Well, in 1943, Jewish populations were being rounded up all over Europe. Denmark was no exception, but efforts by Bohr and others enabled the majority of the relatively small Jewish population to escape by small boats over the narrow strait between Denmark and Sweden. Word came to Bohr about September 1st via the underground that the Germans were planning to arrest him and his family in the next day or two. So they joined the flotilla of small boats and separately or as pairs made the trip to Sweden over 2 nights. Bohr had been in touch through the underground with Chadwick, who was at work on the English half of the English-U.S. Manhattan Project to harness nuclear energy. So the very next night, Bohr boarded a British lightweight Mosquito bomber and made the flight in the bomb bay of that bomber to London. Oops. Yeah. His son O joined him a couple nights later, and the two of them spent some time in London before flying on to the U.S. to join the Manhattan Project. One problem with this method of transportation to England is that the communication with the pilots was through a radio telephone, and Bohr's helmet didn't fit very well, and so he didn't get the message, and also didn't get the oxygen. And so, as they took off and flew high over Norway to avoid German Luftwaffe, he passed out, and only came through as they descended lower into England, but he did make it. He made it there safely. So, Bohr, after spending some time in London, flew on to the United States to join the Manhattan Project in New York. The latter as part of the British Party in Los Alamos, where the bomb was actually being assembled. So he and his son spent 8 months at Los Alamos. While in the U.S. and England, Bohr worked to gain access to the country's leaders, Roosevelt and Churchill. And he did manage to get hour-long audiences with each of them to make his pitch for wide sharing of information on the nuclear energy development, nuclear bomb progress, including with other countries, especially our apparent ally, Russia. Roosevelt was cordial and seemed sympathetic to Bohr's plea. But Churchill was adamant about maintaining the secrecy of the work and maintain and the U.S.-Britain monopoly on the technology. As noted here in this report, in May of '44, Bohr met Churchill and warned him of the dangers of post-war arms race. The meeting was a disaster. Bohr had a similarly fruitless meeting with FDR. Both leaders wanted nothing to do with Bohr's ideas. Or, as we see over on the right, he scolded us like two schoolboys after his meeting with Churchill. So, his, in 1950, he wrote an 8-page open letter to the United Nations, and a couple of paragraphs from that communication wrap up his description of his involvement in the nuclear developments in the U.S. Until the end of the war, I endeavored by every way open to a scientist to stress the importance of appreciating the full political implications of the project and to advocate that before there could be any question of use of atomic weapons, international cooperation be initiated on the elimination of the new menaces to world security. I left America in June of 1945, before the final test of the atom bomb, and remained in England until the official announcement in August of '45 that the weapon had been used. Soon thereafter, I returned to Denmark and have since had no connection with any secret military or industrial project in the field of atomic energy. This photo of the Bohr family on his 70th birthday in 1955 shows Margaret and Niels Bohr surrounded by their 4 sons, their spouses, and the 11 Bohr grandchildren. A picture of tranquility of a normal, happy family living in peace and comfort after several turbulent years. I note parenthetically that my parents, like Bohr, had 4 sons. I was the youngest of those, and each of us married, and each of us had some children, and there were 11 grandchildren. That's a irrelevant coincidence, but I found it interesting. But Bohr continued to serve as director of the Institute and participate fully in its affairs. He also organized the Atoms for Peace Conference in Geneva in 1955, and he helped significantly to establish CERN, the European Organization for Nuclear Research, on the Swiss-French border near Geneva, after considering trying to locate it in Copenhagen. Bohr suffered a stroke in 1962 and died within hours at 77. A golden anniversary celebration, which had been planned for the 50th anniversary of his 1913 publication of the atom, his model of the atom, was celebrated at the Institute in 1963 after his death. And his son, old Bohr, succeeded him as director of the Institute. He, by the way, was a successful physicist and won a Nobel Prize in Physics in 1975. So I would like to close this discussion of Niels Bohr and his contributions to our understanding of the atom with Robert Oppenheimer's evaluation of the era that created our new insight into the world of the atom. The atomic revolution was not the work of one person, but depended on collaboration between scores of researchers in many different countries. Still, from first to last, it was Niels Bohr's original, creative, penetrating, and critical spirit which guided, defined, elaborated, and finally transformed the entire work. That's it. I'm happy to try to answer any questions.
The gentleman sitting between Churchill and FDR, Mr. King, is he Canadian or who was he?
No, that was Bohr. That was Bohr.
No, it wasn't Bohr.
But the label was
It said it was Mr. King. Is he the Canadian Prime Minister?
I must confess, I'm not sure. What does it say? Can you?
William Mackenzie King.
Well, that's Churchill, that's Roosevelt, obviously, and it would make sense this was in Quebec.
King. Mackenzie King.
Yeah.
I think he was Mackenzie King.
Prime Minister, I think.
At that time? Yeah.
Luther,
Yeah.
what do you attribute Churchill and Roosevelt's hostility toward Bohr's ideas about the post-war arms race
Well,
and so on?
Question, what do I attribute Churchill's opposition to wide sharing of the information? They were hell-bent on winning the war, or surviving, in the case of England, surviving, I think, and were not interested in the longer term, because it was clear that it wouldn't be long before any other major industrial country would acquire or be able to develop the technology that was being developed to make the bomb. But I think they were really had blinders on, and Churchill was a pretty strong individual and didn't want anybody questioning his authority.
Did Bohr make any distinction between the morality use of the bomb versus nuclear power?
Well, I think I read a portion there that might imply he, like many of the scientists actually involved in the project, argued for a demonstration bomb, shot before doing what we did to Hiroshima and Nagasaki, which I find a little hard to defend, but from the point of view of people about ready to make a landing in Japan, it seemed a nice thing to do, appropriate thing to do. Yeah, and this, the play gets into the serious discussion of the morality of the whole business, and so I think you will find it very interesting on that score. Well, thank you very much. It's a great day out there. The fall colors are just great, so take advantage of it.
There is just no way that our planning committee or our bucketeers can adequately express our gratitude to you and professors like you who are willing to come for the love of teaching and teach us lifelong learners. Flowers by Design has helped us to do a little bit of a thank you to you so that you will remember how much we appreciated your efforts. Thank you so very much for coming today and for all that you and your colleagues do for the bucket courses.
Well, thank you for being an attentive audience.
Next week we will begin the first of a 4-class course by Associate Professor of Music at Grinnell College, Eric McIntyre, and he will be talking about the creative processes in music. I'm happy to announce that we still have several seats available. So if you haven't signed up yet, or you have friends who would like to sign up, you can probably still get in. In the meantime, remember to leave your blue slips of paper on the table in the hallway, and we'll hope to see you next week. Enjoy this beautiful afternoon. Thank you for coming.